Welcome to video 47, which is the final video of the Foundations of Computational Economics course. And here I will be talking about the final exam and the questions and assignments there. Now this presentation is based on the last year's exam, so there's no guarantee that it's going to be identical this year, but it will certainly be very similar. So the instructions from last year were to complete the tasks in the given Jupyter notebook by answering questions and writing code in the cells provided. So it's very similar to your usual weekly assignments or the midterms. The task will be distributed as Jupyter notebooks, and the answers you provide also should be in the Jupyter notebooks. Each task has a number of points associated with it, and all of the points sum up to 100 points. The grade is the total number of points earned. This is pretty straightforward. Started but not completed tasks, and also the task completed with errors, earn partial points as usually. There's 3 hours to complete the exam and compute all of the important and necessary quantities there. And here's the very important part. The completed exam should be committed to your Git and pushed to to GitHub as you do with weekly assignments. For me to be able to see your work and grade it. And if you've made alternative arrangements with me before the exam, then you would use the means of these alternative arrangements. Okay, the structure from the last year's exams was 5 2-points questions, 3 points questions, 4 5-points questions, and 4 10-points questions. If I'm not mistaken, altogether, this is 100 points. And of course, questions and assignments differ in their difficulty. The 2 and 3 points questions are similar. They are elementary or simple questions which require a short answer to be typed or check the knowledge of, and they check the knowledge of some simple facts. So if you know something, if you know the answer, and you should know the answer, then it takes no time. It just takes the time to type a few words to answer each of these questions. The 5 points questions are more elaborate, and they require a line or two of code, or they are something like find a bug in this short piece of code type of questions. Now finally, and this is where you should spend most of the time, are the 10 points questions, which are more elaborate coding tasks. So here you will have to actually develop some code according to the specification. They're very hard on their own, so if you're just seeing this sort of an assignment, it's going to be next to impossible to complete, but they are absolutely doable if you are fluent with the code base of the course. And essentially, you can find appropriate donor code fast enough to be able to copy it over into your exam and modify the code there to perform the task. But this, of course, requires knowledge and understanding of all the code written in the course, which is why this is going to be very hard if you are not well prepared. And with this structure, the exam is open book, as you know, so you can use any resources, all the books, any internet resources. Google is at your service, and searching through the lectures is also possible for you. So to be able to successfully pass this exam and this course, you really have to prepare in terms of knowing and understanding the code base that was developed during the lectures. And the usual mistake is to run out of time, right? Spend too much time on this simple questions and not have enough time to complete any of the coding tasks. Okay, so here are some examples. 2-point question. In Python code, when assigning a value to a variable, how many spaces should be used around the equal sign according to the PEP 8? Well, you should remember what PEP 8 is, and Let me try to imagine that I don't remember it. So then I go in Google PEP8 spaces around equal. Let's see what Google tells me. Stack Overflow. Well, I want to go to the original one. And, browse through this long list of chapters. This is, of course, PEP8 is a style guide for Python code. It's going to take me some time to find what I need here. And therefore, this is the type of question that you should know or maybe skip to save time. The right answer is one space on each side of the equal sign, if I remember correctly. All right, example question 2. How does convergence rate of the value function iterations successive approximations algorithm depend on the coefficient, on the discount coefficient beta? Well, I've mentioned that at least a couple of dozen times during the lectures. And I'm sure you all remember that the closer beta is to 1, the slower is the rate of convergence. You have to express this idea somehow very fast in a few words. Third example question. In NumPy, what arithmetic operations differ between the two-dimensional array type and the matrix type variables? Here, you may want to go back to the NumPy lecture. And we have mentioned that there is this special matrix type in NumPy, although it's been phased out as far as I'm aware. But this is made to specifically represent matrices to make it possible to just write simple arithmetic operations with matrices as you would do on a piece of paper. And the differences are really, hopefully you remember, is in multiplication. But if you don't remember, it's always possible to write this little piece of code. A is some two-dimensional array. This is a matrix. And let's just test a few arithmetic operations. Plus gives the same answer. I'm just doing A plus A and B plus B. Minus is the same. What is this? Multiplication. So here's the difference, right? So A times A, if it's an array, it goes element by element, whereas if it's a matrix, then multiplication written this way actually means matrix multiplication, and we get something completely different, not element by element. The division is element by element for both, and the matrix multiplication has this special sign at, which is the matrix multiplication that we've used throughout the course, and we never really used matrices. But you may come across this type, and you should be aware of this. So the answer is it's the multiplication operation that differs between the two types. All right. Another example of 3 points question. Write the Bellman equation for the infinite horizon formulation of the following problem. Choice variable C, state variables x, y, and z. X and y evolve stochastically with transition densities given here. Instantaneous utility is given by the utility of C and y. Motion rules for variable z can be left unspecified in the Bellman equation. Right, so we have to, how do you approach this? Here you will have to type some math, and I think the fastest way to do it is to open the lecture notebook with the Bellman equation and copy it from there. But the essential part is to remember where the, in the general Bellman, where does state variables go, choice variable, where does it go, and what to do with this transition densities. You should realize that the infinite horizon means that we don't have time subscripts, and instead the next period variables are usually marked with these primes. And so this basically gives us the PDF for the transition of x prime and of y prime, which are conditional on the other variables, and they should go into the calculation of the expectation in the Bellman equation, right? So the answer looks something like this. We have the general structure of the Bellman equation. value function next time period, the maximization with respect to the choice variables. The state variables are here. Of course, the utility, the instantaneous utility, takes its place where it usually does. The expectation, since we're given the PDFs over here, then we can write the expectation as a double integral with the appropriate d's, and the densities go where they would be in order to calculate the expectation. All right, so to do this, you have to remember the general structure of the Bellman equation and do a little bit of thinking about this transitional PDFs. That's not exactly, that's not something that we encountered just like that. It really checks your knowledge and understanding of the general structure of the Bellman equation. And if you write a Bellman operator here, it's going to be fine as well. Okay, moving on to the question with 5 points. Write a list comprehension expression to produce pairs of squares and cubes of all integers between 1 and 10 inclusive. Okay, inclusive. Well, here you have to remember what a list comprehension is. And this is a Python way of creating lists in a loop. So C, it requires you a little bit of coding here, but it's really just one line. And you have to remember what list comprehension is and think maybe a little bit about how to produce pairs of squares and cubes. So pairs usually means either a list with 2 elements, but more often it's just a tuple. The pair is a tuple. Either implementation would do, but tuple is better. Okay, so here we are. Here's my implementation. The list comprehension, of course, is just this expression here. We have to produce a tuple of cubes, squares and cubes for axes in range. And it's important not to make a mistake here. Inclusive from 0 to 10 means that range should have 2 arguments, 1 and 11. And you can check yourself, of course, to see this. Oops. This is just one variable, so the separator will not work, but that's all right. See, it's a list of tuples. 1, 1, 4, 8, 9, 27 cubes. Square and cube, yeah, that's all right. Okay, see, even though it's 5 points, it's not gonna. It wouldn't take you too much time if you read the code in the course where we use this list comprehensions everywhere. All right, another question for 5 points. The code below outputs a negative value. This is strange because it calculates an average of the powers of 2, which are all positive numbers. Explain what is going on and fix the bug with minimal change to the code. So minimal change is emphasized here, and it's interesting, you know, what the minimum change would be here. So here's the code. It's really simple. We're importing NumPy. We are creating an array, right? These are the powers, 200. We take 2 to the power to some large powers, and then we're computing the mean. Just as it says in the description here, it calculates an average of powers of 2. Average of powers of 2. Right? So these are powers of 2, and we're calculating the average, and just print it instead of returning or anything. And the return is minus 2.56. Isn't that strange? Well, this is a 5 points question, and you have to explain what is going on and fix the bug with minimal change to the code. Minimal change and explain what's going on. Well, this is a really nice problem. So why don't you think about how this is solved on your own? I'm not going to give out the answer to this one, but this is a good example of a 0.5 question. It really requires some thinking, but then very little coding. This is an example of these questions or assignments where you have to find and fix the bug. Okay, moving on to 10 points question. Here's one. Derive your own algorithm and implement it in a function that takes an integer decimal number and outputs its binary representation. Write your code in the cell below and run the test cases. So we need to write some code here. And your own algorithm is emphasized here, which basically is the way of saying that it's not going to be good if you Google something and copy it in. And I can tell you from experience that this is very easy to detect if you've done that. Implement it in a function that takes an integer decimal number and outputs its binary representation. So here we are. This is the cell after the task. We need to write some code here and return something. It's a good example to write. To read what's already written in the coding section. So here it says input integer in decimal, output vector of 0 and 1 to represent the input in binary. Now, what is a vector? Maybe you want to import NumPy and output the NP array to represent the vector. Maybe you look here and you can see that this hints for a list, which is fine. It can be a list as well. And in fact, you know, if you're accurate and if you're careful and you read the task completely and look at the signs like this and sort of add your code to here, not to change the lines which are already written, and sort of continue developing the code as it was started. That's what I should say. That's going to earn more points. So here's an answer. Actually, here it's here's an instructive to show you what I'm thinking of a good answer. Docstring, this is a function, right? So we are trying to write nice readable code. This is a function, so it should have a docstring. We are trying, or at least I'm trying, to follow POP8 standards. I'm outputting the list over here, right? You know, I'm trying to come up and implement a nice algorithm. You know, using not more lines than needed. So what's going on here? We're initializing the list to which we append the new each new digit. The digits are, of course, given by this remainder formula or modulus division, and then you can organize the algorithm into a loop by reassigning x to its half on every step, and now when by integer division, and then when x is 0, then you just return the whole number. But it would be nice to put the larger digits to the left, and the lower digits to the right, and so we reverse the list by doing a slice. And to check myself, I've added these lines, right, which output all the numbers up to 32, and then this checks should also pass, or should also produce the results that are good for checking your code. Now, you know, this is just convenient for me to grade your work, and so it's a bad idea to change anything here, because I will detect that as well, of course. Okay, so this is the check for the code. 0, 1, 2, 3, it's 1, 1, 4 is 1, 0, 0. Yeah, that seems to be okay. And it should end at all ones for 31. That's right. So 2 to the power 5 is 32, so 31 is expressed in 5 digits. And so here are some test cases. All right. Finally, here's an example of a complicated question, really elaborate question for 10 points. Oh, there's some trouble here. So if you see some sort of, how about I remove these? Completely. So if there are inaccuracies and inconsistencies in the questions or trouble, troubles with typing like that, it's a good idea to ask me by writing an email, and I will be monitoring my mail in the morning of the exam. But even a better idea is to interpret these ambiguities to your advantage, and make a little comment, a short comment, to save time. Time is your priority in the exam. And I will treat the ambiguities as something that you can choose and interpret whichever way you find useful. Oh, there is a $10 in here, so it should work like that, but it doesn't. Very strange. I'm not completely sure what's going on here. There. Who knew? Okay, so what's the task? Consider the consumption savings problem in the infinite horizon. Well, you should immediately think of Deaton's class. Each period, the agent chooses how much to consume from the cash in hand M without borrowing. So standard Deaton. The amount remaining after consumption grows stochastically with the gross return taken one of 5 values presented in the table below, independently distributed across time. Okay, so the return is stochastic, not the income, like we had in all of our examples. In addition, each period the agent receives a non-stochastic governmental support payment of $10,000. Okay, so income is deterministic. That's different from what we had in the lectures, but the structure of the solution and all of the code with the model should be the same. Although now it's return, which is stochastic. Returns on savings and the letter payment are the only sources of income. So again, it's a standard. Other than stochastic return, a standard model. The instantaneous utility of consumption is given by utility of which is log. Fine, that's standard. And now stochastic gross returns on savings are given by a finite distribution, discrete random variable. Interesting. So here you have to do a little bit of thinking and realize that when a random income in our models that we've looked at in the model that we've worked with was a continuous random variable, we had to calculate the integral of the next period value, right? We had to calculate the expectation of the value function. Now, this expectation is not an integral; it's just a sum with the appropriate probabilities. So essentially, the work is to replace the quadrature points and quadrature weights with the numbers given in this table. These would be the points, and this would be the weights. And also replace the calculation of the next period's wealth to work with stochastic return rather than stochastic income. Okay, it asks for writing a Bellman equation of the problem, and this is important to check your understanding of how the maximization and optimization and expectation operations nest each other. If you followed and reviewed the Deaton's model, this shouldn't take any problem at all. And then write the code to solve the problem and plot the value function and the optimal policy function, assuming that the choices are made in the discrete grid, with step 1 and the upper bound of the problem is set to 200. Now, this prescribes exactly how to solve the problem, right? The choices are made on the discrete grid with step of $1 or $1,000. So the solver would be a discretized solver, right? That's part of the Deaton's class, but you don't. You can copy it. You can only leave that solver and sort of delete everything else from the Deaton's class. and just form it up to the specification. So this essentially gives you the grid for the choice variable to use. Okay, and again, if you've prepared, if you come to the exam prepared and you've reviewed the Detons class and followed all of the work with that piece of code, then it shouldn't be too hard to cut and paste the relevant sections from that code and modify them according to this new specification of the stochastic element, and also change the stochastic income to stochastic return. Although it's not elementary, I admit, but it's certainly achievable from the code that we have developed in the lectures. Okay, this is the last example of the exam assignment. I wish you all good luck, and remember to manage your time. This is the end of the course. I hope to see you in the applications of the methods that we've learned here.